So as I mentioned at the end of the last lecture, we're going to break it way, way down in this lecture, in that we're going to go all the way down to an atom and even subatomic particles. So we're operating on a much, much smaller scale than we have been in the last several weeks. And we're doing this because we are trying to understand macromolecules, which are large, large molecules, so large bonds of atoms together that make up compounds that are integral to our life. And so we're going to do a quick little 15 minutes of chemistry to get everybody up to speed on what atoms are and elements are, and protons and neutrons and electrons, and just giving the real basics of chemistry. I'm sure that this is all review, but it's important to hear it in English and understand what's going on. So this is an atom. This is an atom of carbon. And an atom is the smallest divisible unit of an element. And so an element is a singular substance that has a unique group of properties that can be no further divided while retaining um, its properties, retaining that atom's um, structure. So we are going to now break down what protons, neutrons, and electrons are, the standard subatomic particles. So starting with protons in the blue here, protons are probably the most thought of subatomic particle. They have a positive charge and they're located in the nucleus, so located in this center of our atom. And they are relatively massive. They have a relatively high mass of one atomic mass unit, which is this unit here. It's measured by the mass of one proton, which is why it's 1 AMU for protons. The second subatomic particle is here in red, and this is a neutron. A neutron has a neutral charge, and it's also located here in the center of our atom, in the nucleus. And it has 1 AMU as well. So it is the same mass as our proton. So why would we have this particle that is neutrally charged? It doesn't really do anything besides add mass to our atom. And the reason we have neutrons is because, um, as we know, like charges repel one another. And so if there were no neutrons, then the nucleus would be made up entirely of protons. And positive charges don't like to be together. And so they would end up repelling one another, and we would have no such thing as a nucleus. They would end up kind of spread everywhere because they were trying to repel each other. So the neutron in the nucleus allows for the nucleus to stay together because it separates those positive charges enough for the nucleus to remain one solid entity. Then we have electrons, which are our last subatomic particle. and electrons have a negative charge. So even though they're different than protons, they have exactly the same charge. So one proton exactly neutralizes one electron. The positive and negative charge are the same magnitude. Electrons are really different than protons and neutrons. Protons and neutrons tend to be pretty stable. They hang out in the nucleus and not much happens with them. But electrons are orbiting. They're all over um, the kind of vicinity of the atom. And they're also really, really little. They're about 1/1800th of the mass of a proton or a neutron. So they're very, very small in comparison. They are also responsible for a lot of the bonding that happens between atoms in order to make molecules. So we are going to look at the periodic table, which is probably something that you're familiar with, in order to understand how many protons and neutrons and electrons are in each of the atoms that we're talking about. We're not going to get too far into bonds or types of bonds, so how molecules are made, but I want to remind you the very basics of what atoms are and how they're made up. And so this is the periodic table of elements. It contains all 118 known elements. Um, and when we get down here, these elements are not actually naturally occurring, they're man-made. Um, so we're up to 118. These two might be hypothetical, but we don't know. So in order to break down the periodic table, to use it as a tool, we're going to focus on two values, the atomic number and the average atomic mass. To give a little bit more context, here is the name of the element and the atomic symbol. So that is the shorthand that we use to refer to that element whenever we're writing out equations or creating sketches of molecules and so on. So first, we're going to ask how do we know how many protons an atom has? So if we're looking at the periodic table, it is arranged by how many how many protons that an atom has. So a lithium atom has 3 protons, a beryllium 4, a boron 5, and a carbon 6. So if we look back at our periodic table, this is the way the table is arranged, left to right, starting here with the lowest atomic number and going all the way up to the highest, 118. An atomic number is definitional to an element. So no matter what else happens, if something has 3 protons, then it's a lithium atom. Lithium always has 3 protons. There's no ifs, ands, or buts. That is just the case. So lots of things can happen to a lithium atom, and as long as it still has 3 protons, it's still lithium. That is what it is, and the number of protons really dictates a lot of the activity of a particular element, it's why an element might be a certain color, it's why it might act a certain way, have certain magnetic properties, and so on. Then how do we know how many electrons an atom has? So normally we think of the default being that our atoms are in a neutral state. That is, that the number of protons, so the number of positive charges, equals the number of electrons or negative charges. And remember that the positive charge of a proton is exactly equal to the negative charge of an electron. And so generally, we assume that lithium, an uncharged lithium atom, has 3 protons and 3 electrons. Pretty simple, right? But lithium is actually a pretty unstable element in this configuration. And so most of the time, it actually exists in the lithium plus ion. And so when we say lithium plus, we mean that a lithium atom has 3 protons and 2 electrons. Since it has 3 protons, it's still a lithium atom. But since it has an uneven or an unequal number of protons and and electrons, it is a charged molecule. So there's one more proton, there is electrons, and this leaves us with one extra plus over here. And so ions are critical for creating ionic bonds, which we're not going to talk about today, but ions are really quite important. How about neutrons? How do we know how many neutrons an atom has? So atoms exist with a set number of neutrons, but an element as a whole could have different numbers of neutrons and it's still that element. So as we spoke about in the beginning, sometimes hydrogen doesn't have a neutron. It just has one proton, and that's fine because there's no force trying to force the protons apart from one another. So it doesn't need a neutron, but it can have one. So this is deuterium, which is a form of hydrogen. It's still hydrogen because there's still only one proton. And this is tritium, has 2 neutrons and a proton. It's hanging out. It's just fine. Also good to note that in each of these examples, we have 1 proton, 1 electron, so no charge, 1 proton, no electron, no charge, 1 proton, no electron, no charge. How can we tell from looking at the periodic table what kind of isotopes a certain element might have? So this is the atomic mass, so how much the average isotope of this particular atom weighs. So if you took all of the mass of a particular element on the entire planet and averaged it, you were going to get roughly this number. And so looking at this number, we can think that the common, for instance, common isotopes of carbon are probably primarily around 12, that like the majority of isotopes of carbon are carbon 12. And so carbon 12 means that definitionally we have 6 protons and then 12 minus 6, so the atomic mass minus the 6 protons equals 6 neutrons. So the majority of carbon on Earth has 6 neutrons. Not all of it, but some. There's also carbon-13, which has 7 neutrons, and carbon-14, which has 8. Atomic mass is measured in atomic mass units, and as we discussed earlier, atomic mass units are the same as the mass of a proton. The mass of a proton does not change dependent upon the element. They are all the same. And now, in the second half of our lecture, we're going to move on to talking about macromolecules. So, molecules being the bonds between atoms that end up making up compounds, and really, really big versions that we need to survive.